Hello, in my last class we discussed about SCRs. It is a semi-controlled switch. Why it is a semi-controlled switch? It's because device can be turned on by applying a control signal at the gate, but then you cannot turn it off by applying a control signal at the gate. It is a latching device. Why is a latching device? Control signal at the gate can be withdrawn once the current through the device is higher than the latching. It doesn't require a continuous gate drive. It allows a conduction only when it is forward biased and it is in conduction mode. Okay. So another device that we studied in the previous lecture was a Triac. Functionally, it is equivalent to two thyristors connected anti-parallel. Okay. So it is like this. There are two thyristors connected anti-parallel and a common gate. Functionally is equivalent. I told you that this device can be triggered by making MT2 positive with respect to MT1 and supplying a positive gate current with respect to MT1. Okay, so this condition, both positive, MT22 is positive, Ig is positive with respect to MT1. It can also be triggered by making MT2 negative, Ig negative with respect to MT1. So the VI characteristics, they look like this: positive Ig and a negative Ig. Okay. So what is the difference between an SCR and a Triac? The dV by dt rating for a Triac is less compared to that of a SCR. Triac has a less time to recover as the blocking mode compared to a SCR. Why? See, in the circuit, at any given time, if this device is reverse biased, this gets forward biased. Okay. When this device is turning off, a negative voltage gets applied across it, and this negative voltage forward biases this device. And in case the rate of change of voltage is high, this device may turn on. Okay. So these are the sum of the essential difference between a Triac and a SCR. And next device that we studied was a GTO. It's again a high power device. A 6 kV, 6 kiloampere device is available. It is being manufactured by Mitsubishi. See here, 6 kV, 6 kiloamperes by Mitsubishi. Okay. It has been developed. SCR and Triac, these are semi-controlled switches both, whereas GTO is a fully controlled switch. You can turn on by positive Ig and you can turn off by negative Ig. Okay. GTO has 4-layer structure similar to SCR. What are the differences? I told you that thickness of P2 layer is reduced in order to increase alpha 2, thereby increase in the gain during turn off. See, turn off gain is a function of alpha 2. It is alpha 2 divided by alpha 1 plus alpha 2 minus 1. Okay. Now, the gain can be increased by increasing alpha 2. How do I increase alpha 2? By decreasing the thickness of P2. That is what I told you in my last lecture. What is another essential difference between a GTO and a Triac, or GTO and a SCR? In GTO, gate and cathode structures are highly interdigitated. It is something like this, highly interdigitated. Okay. So, the result is cathode periphery has increased, and even the remote part of the cathode is very near to the gate. That is what I told you. A high power GTO can be seen as a large number of small GTOs in parallel. Okay. So, therefore, it has a very high di by dt rating. Because of the highly gate cathode structure being highly interdigitated, it has a large area is available during conduction, or at the instant of turn on a large area is available. Okay. So, therefore, it has a very high di by dt rating. In other words, GTO can be brought into conduction at a much faster rate, or a turn on snubber, a small inductor is required in series with the device compared to SCR. Okay. What is another feature that has to be taken into account while turn on? A gate current, a continuous gate current should be maintained in the on period. Okay. So, it is something like this. Having turned on the device completely, the gate current can be reduced, but a small current should be maintained continuously. Okay. Because I told you, momentarily if IA falls or the anode current falls, some of the cathode islands may turn off, and subsequently if the anode current increases, the entire area is not available for conduction. So, it may so happen that only a small area that is available, current is the same, so there will be hot spots and device may fail. Okay. Remember, though GTO can be turned off by applying a control signal at the gate, the turn off gain is small. Okay. Turn off gain is small. So, a large current is required to turn off a conducting GTO. Okay. Turn off loss is also high. Why? It is because of the tail current. How do you reduce the turn off loss? Turn off loss can be reduced by reducing the duration for which the tail current falls. Okay. We have seen in the sense when the GTO is turning off, voltage across it is increasing. Okay. But for substantial period, tail current flows through the device, and therefore turn off losses is high. Okay. See, like this, tail current, this is a very high di by dt, and this is the tail current period, and during this period voltage across the device has risen to quite a high value. Okay. There will be turn off losses will be high. How will you reduce this tail current, or what is the reason for this tail current? It is due to the minority carriers in N1 layer. Okay. So, the duration of tail current can be reduced by penetrating this a highly doped N layer in the P layer. Okay. See N layer is penetrating at regular intervals in the P layer, and it is directly in contact with N minus layer, okay. And because of this, the tail current or the duration for which the tail current flows reduces. Okay. But then this structure cannot block a negative voltage. Okay. This is also known as the anode short structure. Whereas this can block a negative voltage because of junction J1, whereas here junction J1 or N plus is directly in contact with N minus junction J1, so it cannot block negative voltage, whereas this device can block a negative voltage. What is another point that we discussed? The inductance in the loop formed by GTO and the turn of snubber should be very small. Say this, the loop inductance should be very small. Why? It's because of this loop inductance, when you turn off GTO, the current does not get transferred to the snubber. Okay. So there's going to be a large voltage spike. Okay. So this inductance should be very small. In other words, snubber layout is very important. I'll show you a GTO manufactured by Toshiba, a 600 ampere device, gate terminal, okay, and we need to use two heat sinks. It's like formed a sandwich in between two heat sinks. A 600 ampere GTO. Okay, so that's about a GTO. So we have studied SCR, Triac, and GTO. The fourth one, a BJT, bipolar junction transistor. I told you that it was developed in 1948, and in 1975 a 300 volt 400 amp giant transistor was developed by Toshiba. See here, in 1975 a 300 volt 400 ampere giant transistor by Toshiba. Power transistors are normally of NPN type, okay, and the N layer which forms the collector is the thickest one, okay, because that the N layer has to block the voltage. Can you block the reverse voltage? Base emitter or emitter junction is highly doped, so therefore the breakdown voltage of the base emitter junction is very small. So therefore reverse blocking capability is small. Okay. Invariably BJTs in power electronic circuits are operated either in saturation, not deep in saturation, just at the edge of the saturation, and in cutoff. Okay. Definitely not in active. Definitely not in active, because in active power loss that is taking place, the device is high. Okay. Generally, for high voltage BJT, current gain is low. and especially it is operated in saturation. See, in saturation collector current no longer equal to beta into IB, where beta is the gain in the when it is operating in active mode. In saturation, how do you determine the collector current? IC is equal to VCC minus VCE sat divided by RL. So, in this circuit, assume that this BJT is operating in saturation. IC is VCC minus VCE sat divided by R, okay, and it is not equal to beta into IB, where beta is the gain when it is operating in active mode or active region. Okay. First of all, high voltage BJT's current gain is low and it is operated in saturation. So, as the collector current increases, the base current requirement also increases. So, how do I overcome this limitation? Use a Darlington circuit. What is the Darlington circuit? So, it is shown here, 2 transistors or more than 2 connected in this fashion. Okay. Now, what is the gain of this combination? IC is the total current, IC1 is flowing through transistor 1 and IC2 is flowing through transistor 2. Okay. So, total IC is IC1 plus IC2, and what is IC1? Is beta 1 into IB1. Some IB1 is flowing into the base of transistor 1 and I am measuring some beta. Definitely it is not the same beta of the transistor when it is operating in active mode. Okay. So, beta 1 into IB1 is IC1. Similarly, IC2 is some beta 2 into IB2. This is the base current, IB2. But then what is IB2? IB2 is same as the emitter current of transistor 1, IE1. And what is the relationship between IE1 and IB1? It is beta plus 1 into IB1. Okay. Now, you substitute this value in this equation, what do you get? You will get beta 1 plus beta 2 plus B1 beta 1 beta 2 into IB1. So, the overall gain here is beta 1 plus beta 2 plus beta 1 into beta 2. So, therefore, for the same IC, I require a very small base current that has to be supplied to transistor 1. But then what is the disadvantage here? Can I operate T2 in saturation? Answer is no. Why? Say in this circuit, what is VCE2? VCE2 is equal to VBE2, okay, plus VCE1. Okay. VBE2 plus VCE1 is equal to VE2. I am assuming VBE2 of the order of 0.7 volts. Okay. I am assuming. And I am assuming that transistor T1 is in saturation. So, the voltage across the transistor 2, that is VCE2, equal to VCE sat of transistor 1 plus VBE2. Okay. So therefore, it may not be possible to operate transistor 2 in saturation. Okay. So therefore, the losses taking place in the final transistor or transistor 2 here are high. Okay. So that is a disadvantage. Now, how about the safe operating area of the device when it is in forward biased mode or when it is conduction mode? So it is here. On state safe operating area or forward biased safe operating area, FBSOA. Maybe in my second or third lecture, while discussing the ideal switch, I said we drew 3 limits. One is current that is flowing through the device, voltage through the device, voltage across the device, and another one is a power limit. Okay. But if you see for a BJT, there are 4 limits. IC versus VCE. So if you see AB, it is the admissible current IC in steady state. Okay. So a device can carry this much of current till the voltage across it is maybe of this value. Okay. Beyond that point, there is another boundary, BC. It is the maximum power that the transistor can dissipate. Okay. This is the maximum power that the transistor can dissipate. And CD is due to the secondary breakdown. While secondary breakdown, what do you mean by secondary breakdown? I will explain to you. Okay. BC is the maximum power that the device can dissipate. It assumes that a uniform current density in the various transistor regions. Okay. So BC limit assumes that a uniform current density throughout. Let me tell you one thing, it's just not possible to achieve this. Transistor is a minority carrier device. It has a negative resistance coefficient. It's a property. BJT has a negative minority carrier device, therefore it has a negative resistance coefficient. So in other words, as the temperature increases, resistance comes down. See, this is one way to explain, or the reason for having a negative resistance coefficient is this. The minority carrier density in the transistor, okay, the minority carrier density is proportional to the intrinsic current density, okay, and which increases exponentially with the temperature. Okay. Since it is a BJT is a minority carrier device, it has a negative resistance coefficient, and because of this. Okay. So since it has a negative resistance coefficient, paralleling two transistors is difficult. For that matter, any device which has a negative resistance coefficient, paralleling is difficult. Okay. Why it is difficult? See, I will just explain to you. I have connected two resistors in parallel. Assume that one of them has a negative resistance coefficient. Okay. Because of the temperature rise, R1 has decreased by a small value, R1 minus delta R1. Okay. So there is a slight decrease in the resistance. Now these two are in parallel, so smaller the resistance, higher is the current that it will carry. So current that is flowing through R1 will increase. Okay. As the current in the R1 increases, power dissipated in R1 increases. Okay. Now the power dissipated in R1 increases, temperature increases. Okay. Now if temperature increases, again there is a reduction in the resistance because it has a negative resistance coefficient. Okay. So there is going to be again a reduction in the total resistance of R1. So thereby it starts carrying more current. So it goes on building up and eventually it will fail. Okay. So therefore any device which has a negative resistance coefficient, paralleling is difficult. Okay. So that's about the secondary breakdown, and this is due to the minority carrier device. And the last one is a DE. E is a maximum voltage that the device can sustain, DO. Okay. This is for a steady state or continuous current. And in case if the transistor is on for a very short duration, the boundaries of SOI expand. See here, this dotted for the device when it is on for a very short duration, because if the device is on for a very short duration, okay, temperature rise or power dissipation limit can also be increased. Okay. Now coming to the turn on of the BJT. All of us know it requires a positive IB to turn on. Okay. So here is the waveforms. Okay. See, in the on period there are two values of IB. I will tell you sometime later the reason for this. A positive IB is applied to the base, okay, but then the collector current does not start increasing immediately. Okay. It takes some time, what is known as the delay time. Okay. Okay. During TD, though you have applied a positive IB, IC is 0. Okay. And VCC is the rated. Okay. After TD, IC collector current starts increasing, okay, and the collector voltage stops falling, and this increase in current is determined by the load circuit or the external circuit. Okay. So the total on time is TD plus TR, the delay time and the rise time. Okay. This total T on time should be as small as possible. So how do you reduce this T on? T on can be reduced by momentarily supplying a high current at the base. Okay. So that is the reason at this point or during this period, during on period, a high current is flowing through to the base, into the base. Okay. This value is approximately 1.5 times this value, okay, 1.5 times. But then why IB should be reduced after T on? Why can't you maintain the same IB? If you maintain the same IB, transistor may go into deep into saturation. Okay. So that has to be avoided. Why that is to be avoided, we will study in the turn-off process. Okay. So when the device is turned on, if you see, VCE has dropped down to a very low value. Of course, definitely not equal to 0. It is VCE sat. A good power transistor, this value could be of the order of 2 volts. So on state power loss is VCE sat multiplied by IC. That is the on state power loss. Okay. So it is mentioned here. In order to reduce the T on period supply, the base current, which is equal to 1.5 times the required or the steady state IB. Now coming to turn off. There are, or T off consists of TS, what is known as the storage time, plus the fall time of IC. Similar to GTO, during storage time, though the gate signal or gate current has become negative, IC remains approximately same. Okay. So in other words, TS, the storage time, is the delay between the change of base current from positive to negative and the instant when IC starts reducing. Higher the TS, higher is the total turn off time. So as the T of time increases, you may have to come down on the upper frequency of operation. Okay. So now let us study the operation of a transistor when it is in saturation. Okay. When the transistor is in saturation or in quasi-saturation, the width of the base region increases. Okay. So I will just show you, see in this figure, this is a normal transistor in active region, N, P and a N layer. Okay. This N minus is lightly doped and N plus is highly doped. Okay. And this thickness will determine the maximum voltage that it can block. Okay. So as IB increases, the thickness of N minus layer decreases. See in this figure. Okay. So this layer decreases because you are injecting a large number of charges into the base. Okay. And they get diffused into N minus layer. Okay. This is a quasi-saturation region. Now thickness of N minus layer is reducing. It is a highly resistive layer. Okay. The thickness is reducing, therefore the voltage drop across the transistor VCE also falls. As IB is increased further, this N minus layer completely disappears. And this region or this mode of operation is known as saturation mode. Device is completely saturated or highly saturated. Okay. See, the explanation is given here. Its saturation is equivalent to the p-type doping and an extension of base thickness with a corresponding decrease in n minus. It is this figure wherein there is a reduction in the n minus layer. It is equivalent to p type doping and an extension of base thickness with a corresponding decrease in n minus layer. Now, due to this decrease in n minus, because it is lightly doped, n minus indicates the doping level is low, is a highly resistive layer, so VCE drops for a given IC. And this we know, as the transistor saturates, gain comes down. And as IB is increased further, N1 is completely changed to P type. Okay? And this highly doped N plus layer of the collector prevents the base region from extending further. It cannot, the base region cannot extend further. Okay. So how do I turn off the transistor? It involves the removing of all the stored charge in the transistor. See, during turn on, there is a progressive increase of charges into the base. Okay. Now, the turn off is removing all the stored charges from the base or from the transistor. Now, this can be accomplished by making IB is equal to 0. Just open the base terminal, IB is equal to 0. Transistor will turn off, but then it takes a long time. Okay. Now, instead you make IB negative, a negative base drive. Invariably, a BJT is turned off by applying a negative IB. How much IB should be flowing out of the base to turn off the transistor? See, to turn on the transistor, we supplied a high pulse of current to reduce the on time. Okay. And transistor is operated in almost in the saturation region. In other words, it is just entering the saturation region. Now you want to turn it off. What should be the value of IB? Remember, if prior to turn off, if the transistor is over saturated region, in other words, if the transistor is operating deep into saturation, a large IB should not be applied. A high value of minus IB should not be applied to turn it off. Why? If you apply a large value of minus IB to the base, it will result into the rapid evacuation of carriers from the base. Okay. There is going to be a rapid evacuation of the charges from the base. Therefore, the base emitter junction becomes cut off. But then holes in the collector region require certain time to recombine. And let me tell you one thing, this IB, minus IB has negligible effect on this time. By supplying a minus IB, a rapid evacuation of the carriers from the base has taken place. The base emitter junction has become cut off now. But then those holes which are there in the collector region, they require a certain time to recombine. And minus IB has negligible effect on this time. So therefore, the time or instant when the base emitter junction has become cut off, till this process gets completed, this is equivalent to diode in the reverse recovery mode. See here, From the time base empty junction is in cutoff and the base collector current continues to flow, that is due to the holes, okay, base collector, the operation is equivalent to a diode during TRR or reverse recovery time, okay, and this is also known as the current tail, okay. Invariably during this period Vc is already attained a reasonably high value, okay, almost similar to a GTO. We had current tail there because of the minority carriers in n minus. So during current tail period Vc is high, so therefore losses that are taking place in the device will increase. So if the losses in the device increase, you could have something known as a thermal runaway because of the negative resistance coefficient. So therefore, if the device is operated in saturation, IB should be gradually increased in the negative direction, something like this. High value of IB to reduce the on time or T on at steady state, and it is a gradual increase in the negative direction, okay, a constant value, then afterwards turn it off, okay. This is IB, gradually decreased in the negative direction, okay. Now how do you ensure the transistor does not get into saturation? So there is a trade-off. If the transistor gets deep into saturation, Vc is low, so therefore total losses that are taking place in the device are low. But then as it is driven into saturation, storage time increases, okay. So you have to come down on the frequency of operation, maximum frequency or the switching frequency of the device. Now instead of operating the device deep into saturation, operate somewhere at the edge, what is known as the quasi-saturation. How will you ensure this? There is a network, what is known as the anti-saturation network. It is also known as the Becker clamp, which ensures transistor is always operated in quasi-saturation. See, here is the network, okay. This is the power BJT, okay, and this network, okay, D1, D2, D3, D4. I will explain to you the function of which diode, okay. See, the advantage of operating the transistor in quasi-saturation is that VCE increases slightly, but then the storage time reduces significantly. There is a great reduction in TS, the storage time, okay. Now with this anti-saturation network, what is the value of VCE? VCE gives a measure of the saturation level or degree of saturation of the transistor, okay. See here now, VCE, this voltage, okay, is equal to VBE, okay, plus VD2 plus VD3, these two diode drops, minus this drop, okay. So VBE plus these two diode drops minus this diode drop, it is VCE, okay. So now VCE is maintained at, assuming that all the diodes have same voltage drop when they are conducting. Now Vc is maintained at Vbe plus Vd1, voltage drop across one diode. Okay. Now by connecting more number of diodes in this part, you can increase Vce. I have just connected 2. So by connecting additional diodes in series with D2 or D3, Vce can be increased. Now how this network prevents transistor getting into saturation? Okay. This is one way of analyzing. How does this circuit work? Assume that transistor is off, okay. Entire VCC appears across the device, and now we want to turn on the transistor. A positive IB is being applied to this circuit. See, in this circuit I have used a Becker clamp, a transistor, and here is a small load, okay. A simple circuit to explain the principle. So a positive IB is applied at point X. Okay. This transistor is off. In other words, potential of C with respect to the ground is same as VCC, because there is no current here. This is at Vx. Definitely this voltage is very low. So D1 is reverse biased. Cathode potential is same as VCC, and anode potential is the potential of X, and Vx is very small. So all the current starts flowing through D2 and D3 and into the base. Okay. Transistor turns on, okay, therefore Vce falls. Now in order to reduce the on T-on, I said that 1.5 times IB should be supplied. Okay. So Vce falls when this Vce is equal to Vx minus Vd1, okay, or Vx minus 0.7 volts. I am assuming that voltage drop across D1 is 0.7. We will see what sort of a diode is D1 and what could be the voltage drop across it sometime later. As of now, I will assume that voltage drop across D1 when it is conducting is 0.7 volts. Okay. So when Vce is Vx minus 0.7, D1 starts conducting. Okay. So when D1 starts conducting, a part of IB starts flowing through D1. A part of IB starts flowing D1. So therefore there is a reduction in current that is flowing into the base. Okay. So I will repeat, initially D1 was off, transistor is off, Vce or the collector potential is very high, maybe is equal to Vcc. All the current flows through D1 and all the current flows through D2 and D3 and into the base. As transistor turns on, Vce falls, and when Vce is equal to Vx minus this drop, voltage drop across D1, D1 turns on, a part of the current starts flowing through diode D1 and in this fashion. So there is going to be a automatic reduction of current flowing into D2 and D3. Say second case, a load has varied. See, invariably the base drive circuit is designed in such a way that it supplies the required current for a full load, and load on the load that the transistor was supplying has reduced. In other words, IC has come down. Now, if I supply the same IB, transistor will go into saturation mode. That is what I showed you, those three figures: active, quasi saturation and saturation. As the charges are pumped into the base or increases, N1 layer reduces. Now the load has reduced. If I maintain the same IB, transistor is entering into saturation, VCE falls. But then VCE in this circuit cannot fall below a value which is equal to Vx minus D1. See, in this circuit, at any given time VCE is clamped at Vx minus Vd1. So even if the load has come down, if the load has come down, same IB will not flow. See, transistor is trying to go into saturation, Vc is trying to fall. The moment Vc is trying to fall, D1 turns on, it diverts some of the base current. Okay. So base current gets diverted, and therefore this transistor cannot enter the saturation. Okay. So that is how this Becker clamp works. Why do you require D4? D4 is to supply a negative IB. Negative IB. D1, sorry, D2, D3 for a positive IB, and D4 is for negative IB. Okay. All these current ratings, D1, D2, D3, D4, current ratings are small, because maximum they carry, see, this is a base drive current it has to carry. But then voltage ratings of these diodes are different. D2, D3, D4, these are low voltage, low current diodes, low voltage, low current diodes. Whereas D1 should be a high voltage diode. It should be a high voltage diode, because when the transistor is off, cathode potential is same at VCC. Okay. So D1 has to block the entire VCC. So D1 is a high voltage low current diode, whereas these D2, D3, D4 are low voltage low current diodes. So with this I conclude my today's lecture. Thank you.